Good evening, all. So let us start today's topic. So today's topic is going to be on backtracking and branch and bound. Backtracking and branch and bound. So what exactly is backtracking and branch and bound is that? So you can visualize a graph. So while seeing about graph problems, so we learned what the two different types of traversals we saw, right? So one was the DFT, which was depth first traversal, and other was breadth first traversal. So the DFT model is exactly same as this backtracking algorithm. Okay, and then the BFT is nothing but your branch and bound algorithm. So if you know how to implement this DFT and BFT, any type of backtracking and branch and bound problem with a small modification can be done, can be solved. Okay, that is a basic idea. So in backtracking, so we'll understand these two topics with examples. Okay, so this backtracking and branch and bound are like interchangeable. Interchangeable in the sense wherever you're using backtracking, at that place you can use branch and bound also. So at branch and bound, you can use backtracking also. So both are interchangeable. Okay. So now there should be some specific purpose, right? So when we should use backtracking and when we should branch and bound. Okay. So the purpose is that we use backtracking if we want a single solution for a problem. So there might be multiple solutions for a problem, right? So for example, if you take n queens problem, which you're going to see now. So n queens problem is nothing but you will be given with an n cross n chessboard and n queens. So you have to place all those n queens in the n cross n chessboard in such a way that no two queens will attack each other. Okay. So I'll explain this in detail, but you just understand the problem. So this particular problem will have multiple solutions, right? Okay, there can be different possibilities. Okay, so for placing these queens, so now like what happens is if you want to find a single solution, then you can go for backtracking. Whereas you want to find all the solutions, okay, exhaustively, then you can go for branch and bound. Okay, that is the like main difference. Okay, main purpose wise difference between backtracking and branch and bound. Whereas you can use backtracking also for finding all the solutions. No problem with that. Okay, now let us understand these two algorithms. So the first problem which we're going to see is the n queens problem. Okay, so the problem is that you will be given with an n cross n chessboard. So if suppose if it is a 5 queens problem, so what happens is you'll be given with a 5 cross 5 chessboard and you'll be given with 5 queens. So I hope we all know how queens travel, right? So they travel in all paths. Okay, they take the role of bishop as well as the rook, except for the horse. So they can jump to any location. Any location in the sense like the distance doesn't matter. Okay. So like, do you have any doubts in queen traversal? How the queen travels? All of you know how the queen travels, right? So I hope you have played chess and then you know the movement of a queen. Okay, so you'll be given with a n cross n chessboard. Okay, suppose here n is 5 means 5 cross 5 chessboard would be given and then 5 queens will be given. You have to place these 5 queens in such a way that no two queens will attack each other. Okay, for example, so if I place a queen here, so this entire row is occupied by this queen, right? This is under this queen's control and the entire column is also under this queen's control. and this diagonal is also under this queen's control. So I will not be able to place in the same row, same column, and the diagonal as well. So if I place the second queen over here, this will be under attack by the first queen. So I cannot place. So here if I place, this is also under attack by the first queen. So here also I cannot place. So I can place the second queen over here. So now this is a safe position, right? This queen will not attack this queen. Now, so now placing the third queen. So I cannot place the third queen any of in the first two rows, right? Because they are already occupied. So the first column I cannot place because this queen will attack. Here also I cannot place because this queen will attack in the left direction. Here also I cannot place because the first queen's diagonal position as well as the second queen's column position is same. So I cannot place the queen here. This is not safe. This is also not safe. This is safe. So I can place a third queen here. Okay, like this, I will find this entire solution for this queen, n queen's problem. So now the fourth queen, can I place it here? Yes. Is this position safe for this queen, for the fourth queen? Is this
Yes.
position safe? Yeah, this is safe, right? So this queen also will not attack. This queen also cannot attack. This queen also cannot attack. So this position is safe. So I place the fourth queen. Now let me try to place the fifth queen. So is this position safe? No, right? This queen as well as this queen will attack. This is also not safe. This is also not safe. Whereas this position is safe.
Safe.
So this is one of the solutions, right? Like this, you can try out with lot of other combinations for this n coins problem. Okay, to find out all the solutions, we use this backtracking and branch and bound. So this is, for example, I showed you how to keep it. Now let us see the procedure of this n coins problem using backtracking and branch and bound. So let us start with one coins problem. What is the solution for one coins problem? One coins problem means what? You will be given with a 1x1 chessboard. Okay, and then you will be given with one queen and a 1x1 chessboard. So is it safe to place the queen in that 1x1 chessboard?
Yes.
Yes, right? So no other queens are there. So for one queen's problem, that one position is the solution for this problem. Okay. So for two queens problem, is there any solution for two queens problem?
No, sir.
Yeah. For two queens problem, that's no solution. Why? Because if I place a queen here, okay, so all the other locations are under attack by this queen. So nowhere I can place the second queen. So there is one more position in the first row. Let me try to keep it here. If you place here also, all the other positions are under attack by this queen. So I'll not be able to place a second queen at all. So two queens problem does not have a solution. What about three queens problem? This three queens problem also does not have a solution. Suppose if I keep the queen here, in the second row, I should place the queen only at the third position. Okay. Now this is under attack and these two places are also under attack. Okay. So now if I place the queen at the first box, first cell, I will not have any solution. Let me try by keeping it in the second position, second cell. If I place it here, I cannot keep the second queen at all. Right? So all the three locations are under attack by this queen. So this also doesn't have a solution. If I place a queen here in the third cell, I can place in the second row, first cell. Okay, but whereas in this third row, I will not be able to place any coins, right? Because these two cells are under attack by the second coin, and this cell is under attack by the first coin. Okay, third coin I will not be able to place. So three coins problem also does not have a solution. Okay, now let us go to the four coins problem. So actually the n coins problem starts from four coins problem. Why? Because only from four we have the solution. Except for one also has the solution. Okay, so for this n coins problem, we would be starting from an empty chessboard. Okay, empty chessboard, no coins are placed. Now what we would do is we would try to find out whether we would have a solution by placing a coin in the first cell, in the first row. Okay. So I placed in the first row. Now what happens? Now from after placing this in the first row, I will explore in whether in the second row where I can place a coin. Okay. So I'll explore for the safe position for the queen in the second row in the next step. So first I'll place it here. This position is not safe for the queen. Okay. So what happens? I will backtrack. Okay. So I'll backtrack to the previous. See, all these are function calls. Okay. So from here, I'm making a function call by placing a queen in the first row, first column. Since this is safe, I'm going to the next level. If this was itself not safe, I'll backtrack and check for the other location. This was safe, so I'm proceeding to the next location. Next recursive calls. Okay, these are all recursive calls. Now what I would do is I would backtrack to the previous function and then I will try placing at the second location. I can see that this place is also not safe. So I will block this. I mean, I will backtrack from here. The next I place it over here. Okay, so this particular position seems to be safe. Now what I would do from this position, I will proceed to the next level. Okay, I'll just place it on all these locations and see whether we are getting a solution or not. So now what happens if we place it here? This location is under attack by this queen, right? So I'll backtrack. Now what happens? I'll make a new recursive call, new cell will be there. So I'll make use of this itself. Okay, because it'll become more lengthy, the third row, let's say. Okay, I'll just make use of this itself. Imagine that this is a new function call. Now what happens? It comes here by placing the queen at the second column in the third row and sees that, okay, because the second queen will attack. Similarly, this position not safe. The other position is also not safe. Now what happens is, with respect to this position, I tried in all the four locations in the next row. I was not able to place any of the queens. So from here, I will backtrack to the previous function. And then I will make a new recursive call by placing at the next free location. Understood? So this, I didn't get any solution. So I am backtracking. Okay. So two ways you'll be doing a backtracking. One is if that location is under attack. Okay. Other thing is, if this location is not giving me a solution, I will backtrack. Okay, then I'll explore with the next path. So I placed here, this is safe because the first queen cannot attack. So I'll go to the next level. I place the queen here. What happens? This is not safe. So backtrack. Now I place a queen here. This position is this safe?
Yes.
Yes. This position is safe. Now I can go to the next location, next row. If I place here, it is under attack by first queen as well as the third queen. So this is also not safe. It's also not safe. And this is also not safe. Okay, now what happens with respect to this particular location? So I found that all the four conditions, all the four locations are not safe for the queen to be placed. So I will backtrack to this particular function and then come and check whether the other two positions are safe. Okay, so this is also not safe. This is also not safe. Okay, so I got a question. Sam is asking. So what is the condition for safe or not safe? See, actually, these stars are all queens, and this is a chessboard. A 4x4 chessboard is there. Okay, so Sam, you know how queen moves, right? Or you have any doubt in the queen movement in the chessboard? So actually, a queen can move. Oh, okay, fine. Okay, so I'll explain first how the queen moves. See, suppose I'll take a larger chessboard. So you would have seen an 8x8 chessboard, right? A chessboard. Suppose if I place a queen here, so what happens is this entire row will be blocked by this queen because a queen can travel in horizontal, in vertical, okay, and in diagonal locations, diagonal manner, okay. Okay. So now all these locations are blocked by this queen. Okay. If somewhere in the next row, if I place one more queen here, now what happens? This queen will be under attack by this queen, right? So I cannot place here. This is not safe for this queen to stay here, right? So what I should do? I should find a new position. So this particular position is free in the sense like safe. Now what happens is this queen will have some attacking positions, right? So I should check for all the attacking positions. So let me mark it with a different color. So this is actually overlap. Okay. I'm not going to touch the overlap. Let it be green itself because anyway it is not safe for any other queens to be placed, right? So all horizontal and diagonal positions are blocked. And here, so understood. This is diagonal is being blocked by this queen. Now here, so now wherever I blocked in all the other locations, I'll not be able to place the other coins. Okay, so this particular position is free, right? So I can place a new coin here. So if I place a coin here, so it will, let me take some of the color, gray. Okay, so horizontal, and then vertical, sorry, this is horizontal, left diagonal is done, this one, and then here. See, this diagonal will be under attack by this queen, and this also. Fine. Now, wherever I marked the colors, all those are occupied by the queens. Now I can place a queen over here. So like this, it goes on. Understood, Sam? Sam, we're not able to hear you. Okay, fine. So with this constraint, we're going to find out the solution for the 4 points problem. So now we were in, yeah, this particular location, and we try to place this next row. Yeah. And in none of the 4 positions, see, the first position, it is a attack. Okay. In the second position, it's not an attack, but it is not giving a solution. Okay. Whereas third and fourth positions are under attack. Now, this particular position is not giving me any solution. Now, what happened in the previous row? I tried with all the 4 locations, right? First location, second column, third column, and fourth column. So this is not giving me any solution at all. Now, what I would do is I would backtrack to the initial position, and then now I take up the second location. So I place the queen here. If I place the queen here, so I am trying to find out where I can place a queen in the second row. Sam, can you tell me where should I place the second queen? The second column? Okay. So question is, where should I place the second queen in the second row? First queen, the first in the first row, I place the first queen in this location. So where should I place the second queen? AK. Okay. Yeah. AK. Very good. So it's AK 15. Fine. So these 3 locations are under attack. So I should place here only. Correct answer. So I can block this. I mean, in all these positions, I am doing a backtrack. Okay. I'll come here. Since it's not safe, so I'll backtrack. Then I'll come here. Not safe, backtrack. It's also not safe, backtrack. Now this is safe. So let me make a new matrix. This is safe, right? So from here I can proceed to the next level. So now, is this location safe? Can you place a queen here?
Yes.
Yeah, you can place a queen because this queen also will not attack. This queen also will not attack. So since I place the queen in this first column, the third row, I can go to the next level. Next level means next row. Next row. So can I place the queen here? No. I will backtrack. Okay. And try in the second location. Can I place the queen here? No. Again, this queen will attack or this queen will attack. So backtrack. So I can place the queen here, right? Yes. This is a safe position. Now, once you are able to place a queen at the last row, then it means that you have found out a solution. Understood? Okay, so I'll simply mark this as green. I'll print the solution. So in this configuration, all the four queens are safe. None of the two queens will attack each other. Understood? This is the concept. Like this, what you will do is you will keep on proceeding, okay, till you get all the solutions. Okay, fine. So this is actually backtracking algorithm. Okay, so this is not the stop here. Again, you can backtrack and then try keeping in the second location, third location, and then find for some other solutions. Okay, but actually this is a procedure. Now coming to branch and bound. So if we shoot five queens, we would not be satisfied. Yeah, so if we are having five queens, then we need a 5x5 chessboard. Okay. So five queens definitely cannot be placed in 4x4 chessboard, right? Okay, five queens means 5x5 chessboard. Yeah. Sam, I think some problem with your mic. You're trying to speak, but we're not able to hear you. Okay. So now branch and bound. In branch and bound technique, what we will be doing is we will explore all the possibilities in the particular row. So in backtracking, what did you do? Once we find a particular location which is safe, we immediately jump to the next row, right? Whereas in branch and bound, that is not the case. Once we take a row, we're going to completely explore that row, then we go to the next row. Okay, fine. So there are four possibilities, right? In the first row, there are four possibilities. So I will check whether all the four possibilities, whichever is okay to proceed, I will just proceed. I'll just consider them. So if I place a queen here, so this is safe. So what I would do, this is ready to go to the next level. So I'll just put it inside the queue. Okay, just imagine whatever you did in BFT. Okay, breadth first traversal. So this position is also free, right? So this is also ready to go to the next level. This is also free, ready to go to the next level. This is also free, ready to go to the next level. So from in the first row, we were able to place in all these columns, okay? Because previously no other queens were there, right? So all these four columns are free in the first row. So we can start exploring, going to the next level or next row. Okay? So from this, we are going to explore all the four possibilities. So if I place here, what happens? It is not safe, right? So there is you'll not get any solution if you go to the next level. So what we're going to do? We're going to bound this. Okay, bounding means what? We're just marking that this will not lead to a solution. So further proceeding will not lead to a solution. So you can stop with this itself. Go to the other branches and see whether you have a solution or not. That is what bound means. Okay, you have bound this. Now similarly, you can bound this location as well. Okay, this location is safe, so I will not bound. Not bound means it is ready to go to the next row. Okay, we can explore the next row. One second. From here also we can go to the next row. Now, so we have done all the exploration with respect to the first element, right? So with respect to this element, this is all done. Now taking this element. So these three locations should be bound, right? So they are not going to lead to a solution. So we can bond these three locations. Now this is okay. We can proceed. Okay. And from here, the first location is free, whereas the other three locations need to be bound. Fine. So this is with respect to this configuration. Now the last configuration. So I can place here. So from here I can go to the next level. From this position also I can go to the next level. Whereas the other two locations are not safe. Right? Fine. So these three are with respect to this configuration. And these two are with respect to this configuration. And these two are with respect to this configuration. And these three are with respect to this configuration. Okay, fine. Now we are done with the second level. Now going to the third level. So again, you take this, you explore with all the positions, next possibilities. So this is not safe. So we are bounding this. Okay. And the other three locations are also not safe. They are under attack by this particular queen. So we have bound all the locations. So further proceeding is not going to lead to a solution. So we have bound all the locations. So with respect to this configuration, we won't get any solution. Okay. Now coming to the second configuration. So I cannot place a queen here, not safe. This position is safe, right? You can place a queen here. And these two positions are not safe, right? So these three configurations are with respect to this one. Okay, so we can see that three locations are bound. One location is okay. We can proceed to the next level to see whether solution is available or not. Okay. Now coming to this. So I can place a queen here. So safe. And the other three locations are not safe. Okay, and these two are with respect to this one. Now coming to this. So I cannot place in these three locations, right? These two are under attack by this queen, and this location under attack by this queen. and this is okay, right? This is safe. Now coming to this configuration, this is not safe. This is safe. So it's also not safe, right? This location is safe. Whereas this location is not safe. Understood? So these three are with respect to this configuration. Now the final configuration, the second level. So these three locations are under attack by this, and the last location is also under attack by the first one. That's it. So wherever I have not marked as red, those configurations alone can lead to the next level. Okay, so come this location. So here, the first three positions are not safe. Okay, by the third queen. So this queen also will attack this position. So all the four positions are not safe. So this is not leading to a solution. So this configuration is not leading to a solution. Now coming to this. So I cannot place a queen in the first two locations because these are under attack. So I can place a queen in this third location, right? Here I can place. So I have placed a queen at the fourth row, which means this is a solution, right? So like that, one more position is there. Here I will try to place under attack by the second queen. So block. Okay. So this is with respect to this configuration. Now let us try with this configuration. Can you see the solution is getting approaching, okay, parallelly? Okay. So if we place it here, this is not safe. So block. This is safe, right? So none of the queens will attack this position. So I have found a solution. So this is the second configuration, which gives a solution. And these two locations are not safe. Okay, so this is with respect to this particular configuration. Now coming to this configuration. So I cannot place it here, and these three locations are also not safe. So none of the locations are safe. And that's it, right? So there are only two solutions for this four queens problem, and you can see the solutions. Okay, so the solutions are getting parallelly approached. Okay, we are arriving at the solution parallelly. So that is why I told you that branch and bound can be used to find all the solutions. See, you can see backtracking. In backtracking, what happened? It just focused on getting the first solution, right? So then what it will do is it will go on backtrack and then find the different path to find the next solution. Like that it goes. Whereas here in branch and bound, it is parallelly arriving at the solution. So this is a difference. Okay. Now, so let us see like how to implement this. I'll just give an idea, the pseudocode kind of thing I'll give. You just try to code for this. Okay. Now the thing is, we'll do it using backtracking. Why are you going for backtracking? Because backtracking we can use recursion to implement. Okay. So we know that DFT algorithm will take the stack model, right? We'll make use of a stack. And we also know that functions all use stack for implementation, right? Function use the stack model for, like we saw in the Excel sheet, right? How a function flow would be, and recursion also follows the stack model. So we're going to make use of recursion and then avoid all the push pop operation explicitly, whereas implicitly that will happen. Okay, fine. Let us see the solution. The solution would look very simple, but you have to understand this. That is a problem.
Sam,
Yeah, Sam.
Sam, I just want to make an appeal. The recursion, the one you taught us, I actually understand it very well, but it's like when I have a problem, it's difficult trying to use recursion to solve it directly. So I was thinking if you could recommend some other resources on recursion to me, it will go a long way to deepen my understanding of the concept. I do understand, but like what, how to identify that
Okay.
I could use recursion to solve this problem. I'm having a bit of difficulty with that.
No, no. Like how to approach is like one thing is like if you feel that the problem can be solved using divide and conquer or backtracking, okay, then you can go for recursion. So normal iteration, see, all the iteration problems can be done using recursion also. But why we go for recursion is like a very large problem can be simplified and written in a small piece of code. Okay, and the
That is
internal
true.
calculations, internal function calls and all will be large, but that will be taken care by the system itself, right? So like where to use
That's
recursion is
true.
that like everywhere you can use recursion. Wherever there's looping, you can use recursion. So whatever looping problem is there, that can be converted to recursion. But the thing is, the complex
Okay.
iteration problems can be like it will look simple if it is if you are using recursion. See, one thing to
Mm.
like understand recursion is you
So
need to
can you recommend
trace
can you recommend some extra resources to us to understand it better?
additional resources.
Mm,
Okay, I'll put it in the group.
okay,
Okay, I'll check and put it in
thank
the
you.
group.
I,
Hmm.
it's a nice idea. I really love it, but it's like when you
Hmm.
take a problem and you want to solve with recursion, sometimes you think
Hmm.
you don't even know where to start from.
Yeah.
But it's
So what you
possible.
can do
So
is
I
like
think it's a
you can take any iterative
concept.
problem.
Personally, I want to.
Okay, okay.
Okay.
Any looping problem you take and try to solve it using recursion. That will help. Okay, so you can take any array list problem. Okay.
Okay. Yeah, that's fine. Thanks.
Mhm. Yeah. So for n queens problem, so what all we need is we need n, which is the number of queens, and this is also the number of the size of the chessboard. Okay, n represents number of queens as well as the size of the chessboard. And then we have this x comma y, which is the current position of the queen. So currently where we are placing the queen, that is represented by x comma y. And then we have S, also called as SOL, solution. So this is a list which will contain where the particular, where the previous queens are placed. Okay. That is being tracked by the solution array, solution list. See the solution list, what it will be is, it will be just a normal list. The size of the list is the number of queens. Okay, the size of the list is number of queens. So, and every index represents the row number. Zeroth row, first row, second row, third row. Okay. And this values inside this will represent at which column you're placing the queen. For example, if you take this configuration, so you have 0, okay, at 0th column you placed a queen, so the value would be 0 here. And at the third column you placed a queen, so the value here would be 3. So now you're trying to place a queen at the second location, right? Now what happens? You have the track of what all queens, where all the queens are placed. Using this configuration, you can place in the third position, which is at index 3, index 2. Understood? So this is the solution list. From this list, you can, sorry. So from this list, you can like trace out where all the queens are placed. Based on the locations of the previous queens, you can place the third queen. So that is the solution. And then, mm, yeah, I think that's it. This is enough. Now, so what is the stopping point? Okay. So whenever you enter inside this solution, okay. So what you're going to do is you're going to check whether this particular x5 position is safe to place the queen or not. Okay. So I'll just make a function call and I'll tell you what is the safe function. So is safe of n comma x comma y comma so. So this is safe function. So you're going to like write what is this safe function. Just as of now, understand that this is safe function is going to tell whether is it safe to place a queen at x comma y position based on this configuration. Already, you have kept track of the queens in this solution. Looking at this, tell me whether it is safe or not. That is what this is safe function is going to do. It will return true or false. If it is true, then it is safe. If it is false, then it is not safe. So if it is true, we will proceed. Else we will backtrack, right? Okay. So backtrack is nothing but you don't write an else. That's it. It is like all the functions or all the statements which you're going to write now will come under this if. If none of the statements are there apart from this if, then it will automatically backtrack to the previous location because no other statements are that execute, right? Okay. So now what happens is if it is safe, then I will get inside this if condition. And the first thing I will check is, okay, so it is safe, right? So immediately add it as the solution. Okay. So solution of x is equal to y. Okay. So what is the solution of x is equal to y? In this list, x is in a row number and y is the column number, right? So like, so from this configuration, let's suppose we are proceeding to this configuration. Now for this particular queen, so x is what? 2, y is 1. Okay, x is 2, y is 1. So x5 would be 2 comma 1. Second row, first column. Now what we're telling is this, we have found that this particular position is safe. So soon after knowing that it is safe, what I would do is at xth element, okay, that is the second element of the list, I'm making it as 1. Understood? Which means that at the second row, we are placing the queen at the first column. So that is what happens in this step. Okay, at xth row, we are the element is y, which means that the queen is placed at x comma y position. Okay. Now after doing this, so you can see this is one of the solutions, right? When did we know that it is a solution? If we have placed the queen at the last row, right? We are able to place the queen at the last row, which means that we have arrived at a solution. So what we can do is we can print the solution if, what is the condition here? What would be the value of x is the last row?
3.
X would be
3.
3. With respect to n, what is it with respect to n? n minus 1, right? So here it is 4 cross 4,
Yeah, yes. In minus.
4 points problem. So it is n minus 1. So if x is equal to n minus 1, it means that we have arrived at a solution. Just print the solution. Print of solution list. That's all. Okay. And then you can, okay, can write the else part. So if that is not the last location, so if we are somewhere in the middle. If you're somewhere in the middle, what we do is we will call 4 recursive calls for the 4 points problem. Okay. If it is in general way, it is you have to call n recursive calls by placing it in all the other locations. Okay. So just put a for loop in range of n. Okay. And then call the n coins problem, n coins function. So now we have already placed at xth row. So what should be the next row value?
X plus 1.
Yeah. So xth row is done. So we're going to place the queen at x plus 1th row. See, this row is done, right? So next level means you're going to the next row. So we're going to explore the last row, x plus 1, and you're going to place in all the locations and see, right? So that is kept track in I. So comma I, and then solution array. That's all. Understood? So this is your n queens problem.
So
That's
once
all.
repeat the third line, solution of x is equals to y.
This one. Okay. See, like this statement you understood?
Yeah, we are writing whether it is safe to
Yeah,
place
we are
x
going to
in.
write a function which will tell whether it is safe or not. If it is
Yes.
safe, what we're doing is immediately we are um, storing that particular location in this list. Okay, this is a solution list. Okay, so till this point is done. So once I come here, so what happens? I found that this position is safe. Okay, so this is what? What is the coordinate of this point? 2, comma 1.
Yeah. Yes.
Okay, second row, first column, 2, comma 1. So straight away we can see that this index itself will represent the row number, right? So index itself will represent
Yeah.
the row number. And then we are just storing the column number as the value. Okay, see here 0, comma 0 means what? At the 0th row, we have the, at the 0th column, we have a coin. At the first row, the third column,
Third
we have
column.
the second coin. Yeah,
Yes.
the second row, first column, we have the
First
third
column.
coin. So now, while placing at the 4th row, that is the last, with respect to index is 3rd row, right? We can just refer to this solution list where all the queens are placed. Okay, based on the previous queen locations, I'll be able to check whether each and every location which is safe. So for that is only we're using this solution. Okay.
Okay.
Yeah. So now coming to this is safe function. So can anyone tell what would be the logic of this is safe? See the same thing that we did here. Suppose we are placing a queen over here. So what we should do? We should check whether from each and every queen this particular location is free or not. Okay. So this particular queen can travel in all the vertical locations and in all the horizontal locations. Okay. So like I will check whether this particular queen is not in the same column of the queen. Any of these queens actually, but we'll check it one by one. So first thing is I'll check whether it is not in the same column of this particular queen. If it's the same column, straight away I can tell that it is not safe. Right? If the queen you're going to place it here, then the first queen is directly under, like attacking this queen. Okay, so I can tell that it is not safe. So is the first condition. And now, so anyway, we did not check for horizontal. Why? Because we will be going to the next row, right? We will not be placing any other coin in this row. So we'll just go to the next row and then place the coins. So no point in checking whether it is the same row or not. If you check also, it is an unwanted condition. Okay. So first thing is you'll check whether it is the same column. Second thing is you'll check whether it is in the same diagonal. Okay. So how will you find whether a particular position is falling under the diagonal of this position? I just write the index values, then you'll understand. Oh, sorry. So this is actually the thing. Okay. So now, yeah. So if you see the diagonals, so what is, okay, this is what? This is 3 comma 4, right? First, let us take the right diagonal. So it is 3 comma 4. So what is this value? So I'll just write it here, 3 comma 4. And what is the right diagonal, this particular index value?
5,4.
Yes, 5 comma, sorry, 4 comma 5.
Yes, 4,5.
And the next one, this,
5 comma 6.
yeah. And then the last one, 6 comma 7. And that's it. It's not there. If at all, if it is there, it will be 7 comma 8, right? If it is a larger test board, it will be 7 comma 8. So how can you tell that what is the common property for all these numbers?
+1 in both.
Plus 1 in both, but you have to tell me with respect to
+1 in both the row.
yeah. Sam, I think your network is weak, Sam. +1. See, actually, you have to tell me with respect to the first position.
Row plus 1 is equal to column.
Yes, my network is bad, but
Okay. See, actually, for you have to generalize. So if I give 6 comma 7, you have to tell me that it is falling in the diagonal. You'll not be having the previous values and all, right? Direct value would be 6 comma 7. That's all.
So with the origin, same number is added, no? Like in 6 also the difference is 3 and 7 also the difference is 3.
Correct. So that is the logic. Okay. So if the difference between x and the difference between y both are same, then it is falling under the right diagonal. Understood? See, next value would be 7 comma 8. The difference is 4, right? Here the difference is 1, difference is 2, difference is 3, difference is 4. If the x difference and the y differences are same, then it means it is falling under the same diagonal. Now, what about this is right diagonal? What about the left diagonals? You can write the left diagonals here, 3 comma 4. And what is this one?
4,3.
4 comma 3.
Yeah. Next one. This one.
5,2.
5 comma 2. Yeah. And this one.
6,1.
6 comma 1.
And 7,0.
7 comma 0. Now tell me how to identify whether they are in the same diagonal. I mean left diagonal.
So in this, if you see the x, the difference in x is equal to y. I mean,
Is it so?
yes, 3 plus 4 is 7.
That is sum.
And 4 minus 0 is 4.
so I think it's the row +1, column -1.
Yeah. So you can see that the absolute difference is same, right? See, absolute
Okay.
difference here it is 3, sorry, here it is 1, here it is minus 1. Here it is 2,
Mhm.
here it is minus 2. Here it is 3, here it is minus 3. Okay, 4 is minus 4.
Yes.
The absolute difference is same. And one more property, if you don't know how to find the absolute difference, and one more property is that you can see the sum would be the same. X plus y sum is the same, right? So here x plus y is 4, sorry, 7. 3 plus 4 is 7. 5 plus 2 is 7. 6 plus 1 is 7. 7 plus 0 is also 7. Understood? So here the difference is same. Here the sum is same. That's all. So if you put all these conditions together, you can, and none of the conditions are satisfying, then you can say that the coin is safe. Understood? So now let us write it as a code. So first tell me for the same column, what is the condition? And before that you need to iterate for I in need the index as well. Okay. So I in range of length of solution. Okay, you understood why I'm putting this one? See, I need the index as well. Or okay, sorry, not for range of x. See, why I'm putting range of x is that only till the x position there will be queens, right? See, now suppose I'm going to explore the fourth row, which is the index is 3, right? So only 3 elements should be there already present. Only 3 queens will be already present. Fourth queen, I'm going to place it now. Okay, that is represented by x, right? Understood why I'm putting x here?
Once again, sir.
Okay. See, suppose this, mm, take this configuration. So this configuration is represented here, 0, 0, 1, 3. Now I'm going to place the queen at the second row, with respect to index. Okay. And you can see already 2 queens are placed. So second row means x value is going to be 2 only. Y value is going to change. Okay. So y value would be 0, 1, 2, 3, 4. 0, 1, 2, 3. It is going to change. Whereas the x value is same. Okay. So now what happens is till, okay. So this also represents the number of queens that are already present. Got it? This
Yes,
also
sir.
represents the number of queens that are already present. So for that purpose only, I am writing range of x. Okay. Now, mm, yeah. So I would represent the index of this element, index of the solution array, solution list, and to take that particular value, I'll put SOL of that is the solution of I. Okay. So now tell me how to check whether XY fall under the same column of the um, ith queen. If
X minus Y.
no same column. Here y represents column. Y is equal to
Y should be same.
equal to what? Solution of I, right? Return false. See, why I'm putting this is if y is equal to solution of I. So solution of I, see, we are going to iterate this solution till this point. Solution of I is nothing but the column value at which queen 1 is present. Column value at which queen 2 is present, right? So first I'm taking the first queen. I'm checking whether this column is equal to,
So, but in the first case, it is true now. 0 of 0.
yeah, no. See, what is y? See, suppose you're going to place the coin here. Then what happens? This for this, what happens? X would be 2, Y is 0, right? So for this configuration, X is 2, Y is 0. Now this is equal to Y, right? Y is equal to solution of 0, right? Solution of 0 is also 0 only. So it means what? This particular location is not safe. Okay, that's why I'm returning false. Now Y is equal to 1. So it is not equal to 1 is not equal to 0, right? So first queen's column and second, the third queen's column is not safe. But we haven't checked for diagonal. We have to check for the diagonal. Right? Column wise, it is safe. Next, I will be checking for the diagonal. Likewise, I will check for all the queen's column. So if the queen is present here also, it is not safe, right? The second queen will attack the same column. Understood this? Any doubts in this? Any doubts?
No.
Okay. This is for the same column. Now for the right diagonal, what should we do for right diagonal? Yes. This is I and this is solution of I. And this is X and this is Y. So X minus I is equal to Y minus solution of I.
Solution.
That's all. Okay. So if X minus I is equal to Y minus solution of I, then also return false. Okay. And then if so we can use a sum property. Okay. So if I plus solution of I is equal to X plus Y, then also return false. Understood? If none of the conditions are true, okay, for all the queens that are which are present, then what happens? It will come out of the for loop. So if it comes out of the for loop successfully, then you return true. If it comes out of the for loop means it is safe from all the queens. That's all. This is your is safe function. Understood? Any doubts in this? Any doubts? That's all. See, the code is very small, but you can see how many calculations are being done. See, all these will be coming under the recursive calls. The recursion will take care of all the function calls. Understood? Any doubts? Shall we go to the next problem?
Yes, sir.
Okay. So the next problem which you're going to see is the sum of subsets problem. So the problem states that you would be given with a set of elements. Okay. This can be list or set, tuple, whatever. Okay. Just you have some elements. Random elements. Okay. Not in any order. And you'll be given that target. Okay. Which is nothing but suppose 10 is the target. The problem is you're going to find out all the possible um, subsets, okay, all the possible subset of this A, which will give the sum as T. So for example, if we take 1 plus 4 plus 5 is equal to 10, that is one solution, right? And then you have 1 plus 9, the other solution, okay? And then you have 7 plus 3, another solution. Because you're going to find out all the different solutions available in this, okay? Fine. Any doubts in the statement? This is a problem statement. You're given the set of elements and a target value. So you have to take this subset from this set such that the sum of that subset is equal to T. So this is also a backtracking branch and bound problem. I'll show you the procedure, then we'll come to the code. Okay. So initially you are starting with the empty set. So you can just map this with the n-queens problem. Okay, in n-queens problem, we started with an empty chessboard, right? So here we are starting with the empty set. And then let me take this and write here. This is the input set and then this is the target. Now what you will do is you will start from the first element. So this is going to be a huge tree. Okay, you just understand. And now what you will do is you will check whether this particular element is reaching the target. So till now, whatever elements you have considered, the sum of that elements is equal to target or not. That you are going to check. Okay. There are three conditions. One is it would be equal to the target. If it is somewhere equal, then it means you have found out the solution. So if it is greater than the target, it might exceed the target, right? So it means that if you further proceed, you will not going to arrive with the solution. So you can backtrack. Okay. And one more important constraint is you have all the elements that are positive. Okay. No negative elements are present. Okay. That is an assumption and that is also a part of the solution. See, sorry, part of the problem statement. Okay. So you don't have any negative elements. If you have negative elements, then that stop cannot be done. Again, you have to proceed and check exhaustively. Okay. Fine. So now next, the third condition would be if it is less than. Okay, if the current sum is less than the target sum, then you have to further proceed by taking the next element. So now this falls under the third condition, right? Now the current sum is what? This is one only. There's only one element. The value is also one. The current sum is one. Now this is less than the target, so you take the next element. Now what is the current sum?
5.
5. So again, this is less than the target. So go to the next level. Now the current sum is
10.
10. Yes. So now we can mark this green. Okay. So here also you're going to keep track of the solution array. Okay. So you're going to keep track of the solution using the solution array. So like in n-queens problem, we had a solution array, solution list, right? The same thing here also. The size of the solution list is going to be the size of length of this set. Okay, so what you would do is, whenever you find that there's a possibility for a solution, you keep adding those elements. So there will be replacement happening. Okay, so once it comes back here, backtracks here, and then finds the different path. Okay, at that position, at that situation, what happens? There will be an overwriting happening. Okay, as of now, we have come till here and we have found the solution, right? So once you have found the solution, you can simply print all the values which are present till this point. Okay, now 1, 4, 5 is a solution. Now you have found out a solution. So if we further proceed, if we add 7 to it, anyway it is going to lead to a greater number than the target. So like uh, no need to proceed further with respect to this particular element. We can backtrack and find for some other solutions. Okay, so from 5 we are backtracking to 4 and then coming to the next element, which is 7. See, with respect to 4 we have processed 5. Next is 7, and you can see all these are function calls. Okay, so if we add 7, what would be the current sum?
11. Sorry, 12.
12. Yeah, so it is exceeding the target, right? So what you would do, you would backtrack, come to 4. So next element is 3. So what is the current sum?
8.
8.
8. So it is less than the target, so I can proceed further. So till 3, then after the next elements of 3 are 9 and 8. So this is with respect to 3. Okay, so next level of 3. So if we take 9, so what's the current sum?
12.
No, 8 plus 9,
17. Sorry.
17. Okay, this is not leading to a solution, exceeding the target, so backtrack, and we'll go to 3 and come by taking the element 8. So current sum is 16, right? 8 plus 8, 16.
16.
So this also exceeds, so backtrack to 3. So with respect to 3, we have explored with all possibilities. So again, you are backtracking to 4. So from 4, we have explored till 3, right? So till 3, it is done. Now what happens? Next element it will take, which is 9. Now what will be the current sum? 5 plus 9,
14.
14. So exceeding the target, backtrack. And 8, 5 plus 8,
13.
13. Also exceeding the target, backtrack. So with respect to 4, we have explored all the possibilities, right? So you backtrack to 1. So from 1, we explored with 4. So next possibility is
5.
5. Okay. So 1 plus 5 is 6. So like this you go on. And this would be just for 1. And after that you can imagine. Then it would be starting from, so here we started with 1. Then we would again start with 4 and explore all the possibilities. Then we would again start with 5, explore all the possibilities. So it's going to be a huge tree. Now we understood the flow, right? So this is going to be the flow. Okay. So from 1 we explored with 4, then we'll explore with 5, then with the 7, then with 3, like that it goes on, and we'll go till 8. And then with 1, after exploring all the possibilities, we will backtrack to the empty set and then come with the starting position as 4. Understood? This is the backtracking approach. Any doubts in this? Or you want me to go further, more steps? Okay. Now next what we're going to do is we're going to see for branch and bound. So again, you have to visualize the n queens problem. Okay. So now we have started with an empty set. Okay. We are starting with an empty set. Now, like we will take all the elements which are possibly, which would possibly lead the solution. Okay. Lead to a solution. Now one will lead to a solution because the target is less than 10. Okay. 4 also will lead to a solution. 5, 7, 3, 9, 8. So none of the elements are greater than 10. So there's a possibility that every element could lead to a solution. So everything has been added. Okay, for the ready to go to the next level. Next, with respect to this, the next thing which we'll be taking is 4. So 1 plus 4 will lead to a solution. Sorry, might lead to a solution. And then, so I'll write it together. 5 also will lead to a solution. 9 also will lead to a solution. Sorry, 7 also will lead to a solution. 3. See, all these things are the sum would be less than the target, right? So 1 plus 4, 1 plus 5, 1 plus 7, 1 plus 3, all these are less than target. Now comes 9. So 1 plus 9 is equal to 10. Okay. So I will mark it green as far as I will bound. Okay. I need not go to the next level with respect to 9 and 8. Right. And then from 4, we'll take 5. So 4 plus 5 is 9. So it is not greater than target. So possible. And then is 7. 4 plus 7 is 11. Okay. So it is exceeding the target. So it will not lead to the target. So bound. 4 plus 3 is 7. Possibility is there. 4 plus 9 block bound. 4 plus 8 also bound. Understood? Right? So like this, we're going to write for all the possibilities. And then next level, what happens is going to be 1 plus 4 plus 5. And then 1 plus 5 plus 7. 1 plus 7 plus 3. So like that it goes on. We have to add all the previous values that you have considered. So you need not worry about this branch and bound solution. Why? Because it is going to be like it is going to be very lengthy and also complex. Okay, very complex because you need to understand what should be stored inside the queue. And actually, we will not be storing a single element. We'll be storing a structure. Why? Because a lot of information need to be stored, right? Along with one, we have to store what are the previous values that we have taken, what is the index of the previous value, the current sum. All these things should be gathered together and put it as a single entity and then put inside the queue. So, like, you just understand the concept. No need to worry about the solution using branch and bound. Okay, if you understand the solution using backtracking, that is sufficient as of now. Okay, later once you are familiar with all the concepts, you can explore with the branch and bound solution. That will also be interesting if you implement. So you'll be creating a class for storing the elements, whatever I told you now, and then you'll be using a queue to add the elements and DQ, NQ process, all those things will be, you'll be writing it explicitly. Whereas here, everything will be taken care by recursion. That's the only advantage why we go for recursion. Okay. Now let us see the solution for sum of subsets using backtracking. So in sum of subset, so we need to pass the array. And then,
Sir,
yeah,
sir, earlier you told that in backtracking, we are not concerned about all the solutions. Like in the queen's question, you said that that if the first solution if we get, then we will stop.
no, whereas here we are not stopping.
Yes, whereas in subset we are not stopping. We are still finding this further solutions.
No,
So
no, that is the way in which you write the code. If you want to stop in n queens problem, here also I am not stopping, right? There is no condition to stop the process. This particular procedure will also find all the solutions.
so how is it different from bounce and branch and bounce? There also you have
The-
all possible solutions.
yeah, so you have to write some additional code here to stop. See, I'll tell you how to write that. See, actually, once you find a solution, you can keep track of a flag value.
Okay.
Okay, so
Okay.
you can have a global variable flag which will be equal to 0. You can write if not flag, not flag. Okay, once you find a solution, you can just mark the flag as 1. Okay, so not flag means what? Not, so you can mark it
If flag is
false.
0, that means.
So not false, which means true, right?
Okay.
Okay, once you make this true, what happens if this becomes true? It will not enter inside itself, right? It will directly keep on backtracking.
Okay.
So this code, if you add, then this would become single solution problem. If you remove this, it will become exhaustive solutions. All the solutions will be found out. Even in this case also, you can add this particular piece of code to make it a single solution problem. We'll discuss that.
Okay.
So first is the array, and then uh, okay, the list you are passing. Along with that, you can also pass the number of elements. Let us see if it is needed, and then you can pass the current index. Okay, let x be the current index. Current index means which index element you are processing. Suppose you are processing 5, then x would be 2. Okay, and then we need the current sum and the target sum. Okay, we need the current sum and the target sum. So once you enter inside, what you do is immediately you update the current sum. Plus equal to a of x. Okay, so it will come to the function only if, like, if the previous function has not led to a solution, then it will come to this come to this function, right? So you'll be making recursive calls. See what happens here. So it will come to the next recursive call only if the previous level is not giving a solution and it is less than the target. Then only it will come to the next level, right? Suppose you are in this particular function, what you would do is you will immediately add the current value to the current sum. Okay, 5 you are adding it with the previous current sum. Okay, now what you do after that, okay, you also need to, if you want to keep track of the solution also you can have, and then an index corresponding to the solution. Initially this will be 0, and if you go to next levels, this k will get incrementing. Okay, so solution of k is equal to a of x, and then you increment k because you have already stored the element at kth index. If at all I'm going to store the next element, it would be present at k plus 1th index, right? So I will be passing this k value to the next recursive call. Now what is the stopping condition? If, what is the stopping condition? What's the negative stopping condition?
So CS should be less than TS or equal to
Stopping
TS.
condition. Stopping condition.
Equal to.
CS is greater than TS.
Okay, greater than.
If if current sum is greater than target sum, then don't do anything because this is not going to lead to a solution. Simply return. What's the positive stopping condition? CS is equal to TS. Print of solution. So you have to write, I think some, see till k only elements would be there, right? So you can write a separate function. Comma k. So you can just put a loop and then print all the values in this solution till k. Understood why a separate function? Because solution will not contain all the elements as solution. See here, only 3 elements are there. 1 plus 4 plus 5. So if you print solution, what happens? All the elements will be printed. Some junk files also might be present here, right? So to avoid that, you can just put a loop and then iterate only till k. So only 3 elements will be printed. You can do that, okay? So just a loop. So both these stopping conditions are done. So now what should we do? Currently we are at xth position. Okay, that is suppose if we are passing 4, we'll be at the first position, index 1, right? So we have to start from index 2 and then check whether we are able to get the solution or not. So for that we need to put a for loop, right? So for I in range of, so what is start value? We have processed till x, right? So x plus 1, comma n. So n is the total number of elements. So x plus 1, comma n. So now I'll call the recursive function sum of subset of a comma n comma. In place of x, what should I pass?
X plus 1.
No, it will not be expressed in always, right? So next it will go to the third location, fourth location, like that keeps on increasing.
I.
So that is what is I.
X
Yeah,
plus
very good. Not express I, just I.
Okay.
Okay. So I itself is starting from x plus 1 only. So I only should pass. Comma, current sum, target sum, solution, and then k. See all these values, current sum already we have updated. K also we have updated. So no need to change anything. Directly call this function. That's all. This is your code. See how simple it is, and you can see what work it is doing. So it's just a small part of the iteration. You can imagine if we iterate the entire set of elements. So it is going to be really huge. Okay, so all these will be taken care by these 2 lines. Okay, we are doing a recursive call inside a for loop. So it is very strong. Okay, fine. So any doubts in this?
No, sir.
Okay. So this is about backtracking and branch and bound. So you can try these problems, and there are few more problems as well. Okay. So now I think this is enough for today. We can discuss the other problems in the upcoming classes. And so like today is actually the 21st day. Okay. So all the topics have been covered. From the next class, we'll be starting with the project. Okay. So parallelly, we can also have the doubt sessions, but I think mostly we'll be busy with the projects itself. So like 3 more weeks are there. We'll be doing 1 project per week. Okay. So we'll try to solve 1 project sorry, within 3 days. 3 days in the sense like three
Classes,
um, per week we have 3 classes, right?
3 classes.
So we'll try to finish within these 3 classes. If you're not able to finish within these 3 classes, we might have additional classes. Okay, so we might have the entire week also classes. Okay, so every day we'll be solving problems, and I request you people also to do some homework regarding the project.
Okay.
Okay, so project next class will start.
Okay, sir.
Okay, fine. So thank you all. We can meet in the next class.
Okay. Thank you, sir.